Okay guys, in this next video we're going to be discussing chemical nomenclature, and so we're going to learn the different rules that we need to know for deriving the names and chemical formulas for various inorganic compounds. We are going to start with ions. Okay, so this is pertinent to naming ionic compounds. We need to be familiar with the types of ions that are formed commonly. And in this first slide, we're going to discuss monatomic ions. So these are single atoms that ionize to form an ion. Typically, what we find are that metals form cations and nonmetals form anions. And some of the main group elements, they typically form only one type of ion. And so what I've listed here are the ions for the main group. So we've got group 1 cations. I'm going to go ahead and pull up my periodic table just to point out that the atoms in group 1, that is along this column of the periodic table, they form +1 cations only. So when lithium forms an ion, it forms the lithium plus ion. Sodium, the sodium plus ion. Potassium, potassium plus, and so on. Your group 2 metals, they typically form +2 cations. So beryllium 2 plus, magnesium 2 plus, calcium 2 plus, strontium 2 plus, barium 2 plus. Moving across the periodic table, if we go to group 3, aluminum and gallium, these form +3 cations. And then we're going to go to the other side. Well, let's go ahead and start with the what I've listed here, the heavy main group cations. So these are going to be the metals that are down here. So they have larger atomic masses. These guys typically form 2 different cations. Okay, so for example, indium here in group 3, it forms a 3 plus cation and also a 1 plus cation. Thallium does the same thing. In the next group over, tin forms a 4 plus cation, but also a 2 plus cation. Lead forms a 4 plus cation and a 2 plus cation. Bismuth forms a 5 plus cation and a 3 plus cation. You might notice that there's a pattern here. So if we look at the North American group numbers, so group 1, group 2, group 3, 4, and 5, the group 1 cations, the group 1 metals, they form +1 cations. The group 2 metals +2. The lightweight metals in group 3 form a 3 plus cation. And then the heavier ones, they form a 3 plus cation and then also a 3 minus 2 equals 1 plus cation. For group 4, these heavier atoms at the bottom, tin and lead, it's a 4 plus cation and also a 4 minus 2, a +2 cation. And group 5, it's +3, it's +5 and +3 for bismuth. The transition metals, as it says here, they typically form various types of cations with variable charges. And so really there's no easy way to predict what the charges are for the different cations, and some of them form quite a few different cations. And so there's no specific rules for the transition elements. However, there are 3 transition elements that only form a single ion charge, and that would be zinc, which is always a +2 cation, cadmium, which is always a +2 cation, and silver, which always forms a +1 cation. Turning to the nonmetals, there is also some trends that you see in the ions that they form, the anions. So in your halogens, they always form a -1 cation, or sorry, a -1 anion. The oxygen family, the nonmetals, they form a -2 anion. Nitrogen and phosphorus, typically a -3. Okay, and so I've listed here all of the different anions that you would expect to see commonly. I'll point out one atom, hydrogen. Hydrogen can form a +1 cation, and it can also form a -1 anion. So it kind of goes both ways. How do we name the ions? It's fairly straightforward. For cations that have a unique charge, like sodium, magnesium, and zinc, you simply use the atom name. So it's the sodium ion or the zinc ion. For cations that have variable charges, so for example, iron, it forms a +2 and a +3 cation, you use the so-called stock system, which involves Roman numerals. So we would call the iron 2+, we would call that the iron 2 ion. This iron 3+ is called the iron 3 ion. For anions, the naming scheme is a little bit different. We have to modify the element's name. We typically drop the last few letters of the element's name and add the suffix IDE. So nitrogen, when it forms an anion, a -3 anion, we call it the nitride anion. Phosphorus becomes phosphide. Oxygen becomes oxide. Sulfur becomes sulfide. Hydrogen, when it forms its -1 anion, we call it hydride. Fluorine is called fluoride when it forms an anion, and so on. So this is a list of all of the names that you might encounter here in this course. And so it's useful to take a look at them and make a note of the spelling and practice saying the words. You'll find that really helps you take control, take command of chemical nomenclature. So this is how you name ions. There are also a number of polyatomic ions that you need to be familiar with. And when I say familiar, you need to have them memorized. So there are 3 polyatomic cations that you need to know about. One of them is called the ammonium cation, NH4+. The next one is called the mercury 1 cation, so it's Hg2, so there's 2 mercury atoms, and then that little diatomic mercury molecule has a 2+ charge. So that's the mercury 1 cation. And then this one here, this H3O+, this is a water molecule that has an extra proton attached to it. This is called hydronium. And we'll talk a lot about hydronium when we get to the acid-base topic in a later chapter. So there's only 3 polyatomic cations that we have to worry about in this course, but there's a whole bunch of polyatomic anions. And so on Blackboard, I've got a list of the common polyatomic ions. These involve various prefixes and suffixes. There's also a family of polyatomic anions that are called oxyanions or oxoanions. There's also acid anions. And so there's just a whole bunch that you need to commit to memory. And so I'm going to pull up that list right now and just take you through the structure of this list of ions. So on this table, these 3 tables, we've got the various ions that you need to be familiar with. So here are the cations, the 3 cations that you need to know. You need to know the formula, the charge, and then the name of the ion. There's also several miscellaneous anions that don't have any type of regularity to their name that you just need to commit to memory. One of them is called the cyanide ion, so Cn-. The peroxide ion here, it's a diatomic oxygen molecule with a -2 charge. So this is called peroxide. Hydroxide, which is very important in acid-base chemistry, OH-, you definitely need to know this one. And then here we have a table of oxoanions. And so oxoanions are polyatomic ions that have a central atom. Sometimes it's a nonmetal, sometimes it's a metal. And around those central atoms are various excuse me, are various oxygen atoms, numbers of oxygen atoms, and then the whole species is charged. So here, this group 14, so this refers to oxoanions coming from group 14 of the periodic table. We have the carbonate ion with a -2 charge, the silicate ion also with a -2 charge, and then this species over here, this is the acid anion corresponding to carbonate. So if you take the carbonate ion and you attach a proton to one of those oxygen atoms, you get this acidic anion. And so this is called the hydrogen carbonate ion. So the name is in part based upon the parent oxoanion. Moving over to group 15, so the nitrogen family, we have nitrate, NO3-, and then there's an NO2-, which is called nitrite. And so here's where we are getting into the various suffixes. So we've got ate and ite. Notice that the ate has more oxygen atoms than the ite species. As you go down the periodic table, we also have a phosphate and a phosphite. Notice it's PO4 and PO3, but the charges for phosphate and phosphite are -3. For nitrogen, they are -1. And so you really just have to memorize this as a fact. So people often use flashcards to help them memorize both the formulas and the names of the ions, and I highly recommend that you try that. Continuing down, we have arsenate and arsenite. And then these two entries here in the table, these go back to phosphate. If you take the phosphate ion and you add a proton to it, notice that the charge goes up by 1. And we now call this the hydrogen phosphate ion. You can add another proton to this guy, and that's going to give you the H2PO4-, and that we call the dihydrogen phosphate. Down group 16, we've got sulfate and sulfite, selenate. You can add a proton to the sulfate to give you the hydrogen sulfate ion. You can add a proton to sulfite to give you the hydrogen sulfite ion. In group 17, we've got several families of oxoions. We've got, and here, notice we've got a set of 4 involving chlorine, a set of 4 involving bromine, and a set of 4 involving iodine. And so here we are using both a prefix, per, and hypo, as well as the ATE and ITE suffixes. So, and they're all very similar, right? So when you've got 4 oxygen atoms, it's perchlorate. The next one down with 3 oxygen atoms is chlorate. With only 2 oxygen atoms, it's chlorite. And then with only 1 oxygen atom, it's the hypochlorite ion. And the other families are the same. Okay, they follow the same trend. Here we have another set of miscellaneous oxoanions that have irregular names that you simply need to commit to memory. Here we have OCN-. This is the cyanate ion, acetate, very important ion for us, the oxalate ion, the thiosulfate ion, thiocyanate ion, permanganate, chromate, and dichromate. One tip to help you remember the thiosulfate and the thiocyanate, if you have sulfate memorized, keep in mind that the prefix thio, what that means is to replace an oxygen atom with the sulfur. So if you started with the sulfate ion, to turn the sulfate ion into the thiosulfate ion, you take one of the oxygen atoms and turn it into a sulfur. And that's why it's S2O3. Likewise, you can take the cyanate ion and turn it into the thiocyanate ion by replacing that oxygen with the sulfur. Okay, so there is some meaning to these different prefixes, but for the vast majority of these ions, you simply need to be committing all of this information to memory, flashcards are strongly advised to help you do that. So I'm going to go ahead and put this list away. We'll go back to the lecture slides here. So the next task is to learn how to name ionic compounds. And so these are the 3 rules that you need to know, in addition to having all of those ions memorized. So the cation always comes before the anion in both the formula and the name. When you're writing the chemical formulas, you don't include the charges on the ions. And then when you are generating the formula subscripts, you need to reduce the subscripts to their lowest whole number ratios, but you have to be careful about doing that. So in this example problem, I'm just going to illustrate the process of naming a few ionic compounds to give you a sense of how it works. And then I'll show you a set of worksheets where you can practice this for yourself. So in this first compound, okay, the first thing you want to do is to recognize what type of compound this is. So we see that we've got magnesium and nitrogen present in the compound. Magnesium is a metal, nitrogen is a nonmetal, and so we want to recognize this as an ionic compound. Recall from the previous lecture that ionic compounds involve metals bonded with nonmetals, and so we would use our ionic compound naming rules to figure out what the name is for this compound. So magnesium is a group 2 cation, and group 2 cations are always group 2. So we don't need any Roman numerals when writing down the cation name. We would just simply write magnesium. And then for the nitrogen forms a -3 anion. And the way you write the ion name is you alter the end of the word nitrogen and replace it with the IDE suffix. And so this would be magnesium nitride. For part B, we've got chromium present, and then what you want to recognize, you need to have your common ions memorized so that you will recognize this unit as the sulfate ion. And you know that the sulfate will have a -2 charge. So this is just something that you have to have memorized. You then use the charge on the sulfate, the anion, to figure out what should be the charge on the cation. And so in order for this to be a neutral compound, since sulfate is -2, you would need a +2 charge on the chromium. So then you would have the chromium 2 sulfate. So that would be the name of that compound. Now, why have I used the Roman numerals here for chromium but not for nitrogen? Again, it has to do with the fact that group 2 cations always form a +2 cation, so you don't need to include the Roman numerals to indicate the charge of the cation. However, chromium is a transition metal, and chromium can have all kinds of different charge states. +2 in this case, there's a +3 and a +6, and so you need to distinguish which chromium cation you're talking about, and we do that using these Roman numerals. So when the ion can have a variable charge, you need to use the Roman numerals. But when the ion has a unique charge, you don't use them. For the next one, we have calcium present and oxygen. Again, it's a ionic compound. Calcium's a metal, oxygen is a nonmetal. Calcium is in group 2, and so we don't need the Roman numerals here. We do need to spell it correctly. And then oxygen becomes oxide, like so. For part D, we see that we've got lead, and then we need to recognize this as the chromate ion. chromate has a -2 charge, that means that the lead, which has a variable charge, should be +2. And so we would call this lead 2 chromate. For parts E through G, we're going the other way. We're given the name, and we're being asked to find the chemical formula. So the symbol for iron is Fe, and we're told that this is the iron 2 cation, so we have a +2 charge. Phosphate, we need to have that memorized as that. Now, we have to get rid of the charges, and we need to get the subscripts correct. So we bring the charges down. We'll have Fe3 PO4 2. For part F, titanium 4 oxide. So we're going to have the titanium cation. It has a 4+ charge. Oxide is a 2- charge. We bring those those charges down. We get this intermediate structure that looks like this. Here, we can reduce the subscripts even further. We can write that as TiO2. Finally, the last one, part G here. We've got thallium 3 plus, and then nitrate, which we have to have memorized like that. Bring the charges down. That would be the chemical formula for this one. Before we move on to the molecular compound names, I want to point out that on Blackboard I have a set of worksheets where it's just for you to practice. So there's just a whole bunch of ionic compound names, and you need to figure out what the formulas are. The answers are given at the end of the worksheets. So you do have the answers available to you. So you definitely need to practice this kind of thing. So this first page is going from ionic compound names to their formulas. There's a second page of that as well. And then the third and fourth pages are going from formulas to names. So plenty of opportunity for practice. And then the remaining pages correspond to different types of compounds. And so we'll move on to that part next. So molecular compounds, which are formed between nonmetals, use a different naming system. They use Greek prefixes rather than these ion names that we've been talking about. Here are the rules for naming binary molecular compounds that contain two types of atoms. First, you never ever reduce the subscripts for a molecular compound because that would be a different molecule. You use Greek prefixes to indicate how many atoms there are of a given type. The first species in the compound gets its full atom name, and then the second species gets an IDE suffix. And we often simplify the words. For example, if you have tetraoxide, a compound involving 4 oxygen atoms, you typically will replace that AO with just an O. And so I'll show you that as we go through a couple of examples. You typically put the atoms with in order of increasing nonmetal character, and so this is the ordering for atoms. So boron comes before every other nonmetal that it can form a compound with. Silicon comes before carbon and all of these, but it always goes after boron, and so on. Fortunately, you don't actually need to memorize this list. You will either be given the formula with the correct ordering of atoms in it, or you'll be given the name with the correct ordering of atoms in it. So you don't actually have to memorize the order that's to be used. You do, however, need to know your Greek prefixes for the number of a given atom type. So you need to have at least mono through deca memorized. So let me just show you some examples of this type of compound. So these are all molecular compounds, and the way you know that is that you see it's nonmetals with nonmetals. Okay, so you don't use your ionic compound rules, you use these molecular compound rules. So for this first one, in 2O4, we have 2 nitrogens, and so that would be dinitrogen. So the first atom gets the full name of the element, and then the following atom, you use the suffix IDE. And so since we have 4 oxygens here, it's tetra. But since the AO combination is a little awkward, we just call it tetroxide. For part B, we have tetraphosphorus. And then it's going to be hexoxide because there are six oxygen atoms. For part C, we've got dichlorine. Right, the first atom in the compound gets its full atom name, and then you use the IDE suffix for the second atom. Again, hexoxide in this case. For part D, this would be phosphorus. You can often ignore the prefix mono, except when it's really needed. I know that doesn't help very much. So one way to say this would be phosphorus trichloride, or you could do monophosphorus, and everyone would know what you're talking about. Phosphorus trichloride would also work here. Part E, this would be, I'll go ahead and do monophosphorus. We'll call it pentachloride. Like that. Parts F through I, we're going the other way. So disulfur means you would have 2 sulfurs, and dichloride would mean 2 chlorines. For part G, tetraphosphorus trisulfide, P4S3. For H, carbon disulfide, we'll just assume that the carbon is mono, and that it's S2. Sulfur trioxide, again, monosulfur, and then 3 oxygens, like that. So these are the rules for, this is how you employ the rules for naming molecular compounds. Again, this set of worksheets, it has a whole bunch for you to try, and the answers are at the end of the worksheets. This is both doing names to formulas and formulas to names. You definitely want to be able to practice these so that you know all of your Greek prefixes. We'll move on to the next class of compounds. So these are acids that we'll be naming. Acids are a class of compounds that give protons in water, as well as other anions. And so the oxoacids is a class of acids that are based upon the oxoanions. And so the way that you name these is that you start with the parent oxoanion name, and then you replace ATE with IC. So for example, if you had sulfate, you would add protons to the sulfate ion, and then you would change the word sulfate to sulfuric acid. If you were dealing with sulfite, you would replace the ITE with OUS. So you would take the sulfite ion, you would add protons, and then you would call it sulfurous acid. Let's see, I want to check the next slide here to see if I've got, yes. And so here is examples of doing that. So here I've got various oxo anions that we had from the sheet of common ions. For example, carbonate. How you form the corresponding acid is you add protons to the carbonate ion, so it becomes H2CO3. Notice it's neutral now. And then the ATE becomes IC. So carbonate becomes carbonic acid. Nitrate, add a proton. Nitrate then becomes nitric acid. Nitrite, add a proton, becomes nitrous acid. Okay, so you want to be able to do this for all of the oxoacids that are on, all of the oxo anions that are on your list of common ions. You want to be able to name the corresponding oxoacid. There is another class of acids that we need to be able to name, so-called binary acids, which are derived from binary compounds. Okay, so we start with the binary compound's name, and then we replace the suffix IDE with IC, and we replace the term hydrogen with the hydro prefix. And so let me show you a few examples of that. So here on, we would call this hydrogen fluoride. That's the name of the molecular compound. If you take hydrogen fluoride and dissolve it in water, it becomes hydrofluoric acid. So you replace the word hydrogen with this prefix hydro, and then you replace the IDE with IC. So hydrogen fluoride becomes hydrofluoric acid, hydrogen chloride becomes hydrochloric acid, hydrogen bromide becomes hydrobromic acid, and so on. Okay, so these are actually all of the ones that you need to know as far as these binary acids are concerned. The rest are all oxoacids. Just a couple more points. When you're actually discussing an acid's name, you need to add the word acid to the end of it. And then when you're looking at the formulas to indicate that it's an acid, you use the AQ phase label, which stands for aqueous. That is, the acid is dissolved in water. Okay, and so I'm sure I've got a few examples here. So in this case, we are talking about the oxoacid, the oxoacid corresponding to SeO4. So H2SeO4 is called selenic acid. They're asking us to write down the formula and name of the corresponding parent oxoanion. So here is the acid. To get the parent ion, we remove the protons. Right? Each proton is positively charged, and so if you take off 2 protons, you're going to be left with the -2 charge, and then the IC becomes ATE, selenate. Next, we're looking at perbromic acid. Take off the proton. We get a -1 charge. And then the IC goes back to ATE, perbromate ion. Here we have a bunch of anion names, and they want us to write down the formulas, and they also want us to write down the formulas for the corresponding acids. So I'm just going to go down this list. So the hypoiodite ion is IO-. you add a proton to that. So that's the corresponding acid. I'll even put the phase label. And then the name would be hypoiodous acid. For acetate, here's the formula for acetate. You add a proton to it, and this would be acetic acid. Acetate becomes acetic acid. For the cyanate, we add a proton, and this would be cyanic acid. The thiocyanate ion is SCN minus, add a proton, and then we would have thiocyanic acid. Oxalate C2O42 minus, add 2 protons to this one to make it neutral, and this would be oxalic acid. Like that. So you need to have these common anions memorized, and then to construct the acid names, you need to be able to add a sufficient number of protons to make the species neutral, and then you need to be familiar with your ate to ic, ite to ous name conversions. Another class of compounds are known as hydrates, and so these are ionic compounds that have water molecules, a set number of water molecules, bound within the crystal structure. And the term anhydrous means that there is no water within the crystal structure, and the term hydrate means that there is water embedded in the crystal structure. The way that you write the chemical formula for a hydrate is you use the chemical formula unit for the ionic compound, and then you put a dot with an integer number of water molecules. I guess n doesn't have to be an integer, but it often is. An integer number of water molecules. And the way that you say the name of the hydrate is you use the anhydrous compound's name, so what we've already looked at for ionic compounds, and then you use a Greek prefix in the word hydrate at the end, where the prefix corresponds to the number of hydrogen atoms. And so let's take a quick look at a few hydrates here. So Epsom salts, they have the chemical formula magnesium sulfate with 7 waters embedded in the crystal structure. How would we name that? Well, first you need to come up with the ionic compound's name. So that would be magnesium sulfate. And then 7, the Greek prefix is hepta. Heptahydrate. Like that. For the next one, we've got sodium carbonate. That's the anhydrous compound's name. We've got 10 waters, and so that would be decahydrate. For part C, gypsum, the name is calcium sulfate dihydrate, and so we would do calcium sulfate. Calcium's a +2 cation, sulfate's a -2 anion, dihydrate, 2H2O. For part D, sodium thiosulfate pentahydrate. Sodium is a +1 cation. The thiosulfite S2O3 is a 2- anion. So we're going to have, this is the anhydrous compound's formula, pentahydrate 5H2O. That'll be the chemical formula for this hydrate compound. And with that, we'll go ahead and stop this video.